Okay, let's unpack this. We are diving into a realm where high-performance architecture meets, well, almost molecular science in a way. It's this rigorous quest for truly healthy indoor air. And, for anyone in the building world, or maybe you're just curious about these advanced health metrics and how you ensure the air you breathe inside is actually meticulously cleaner than the air outside, this is your deep dive. Today, we are focusing laser-like on one of the most critical health credits, I think, in the new Sustainable Design Standard, LEED V5.
Hmm.
Specifically, we're dissecting the requirements for the Enhanced Indoor Air Quality Credit. That's EQc1. What does it actually take? What does it take to engineer a building that gets certified for air quality that dramatically exceeds the standard minimums? And crucially, what are these two distinct, pretty complex pathways to actually get there?
That's absolutely right. Our target today is specifically LEED for building design and construction, so
Yeah.
BD+C, new construction, the V5 standard, and yes, that specific credit, EQc1, enhanced air quality, it's worth one possible point.
Just 1 point? Seems like a lot of work for 1 point.
Well, it is, but it's a highly impactful point. And the core intent here, it couldn't be clearer, really. It is explicitly to design for increased indoor air quality IAQ. The overarching goal, better protecting the health and actually optimizing the performance of the people inside the building, the occupants. This is rapidly becoming, I'd say, the frontier of modern building science.
Okay, definitely sounds important. And if you listening want to hear more deep dives just like this one and really explore this world of high-performance design and building science, please do subscribe. It helps us keep digging into these topics. All right, so before a design team can even think about earning that single, crucial, enhanced air quality credit, EQc1, they first have to prove they've satisfied the prerequisites.
Exactly.
You can't attempt the marathon, like you said, until you've successfully walked the necessary distance. So what is the regulatory starting point? What's this baseline standard that has to be exceeded first?
Okay, the foundational requirement is that the building design must first meet and really exceed the standard set by SHRA 62.1 2022,
Right.
specifically Section 6.
SHRA 62.1, Section 6.
Got it.
Right. This section defines the sort of acceptable methods and rates for ventilation and controlling contaminants. In LEED terms, this prerequisite is called EQP2, Fundamental Air Quality. Now, meeting this code, it simply establishes the minimum acceptable air quality for occupancy. It's ensuring basic safety, maybe some odor control.
So the bare minimum, essentially.
Pretty much. But the fascinating part, and this is key, is that the way you choose to meet this fundamental requirement, EQP2, it strategically shapes your path toward the enhanced credit EQc1.
Okay, so there's a critical procedural linkage here that design teams have to wrestle with right up front.
Yes.
It's not just about hitting the baseline number, it's how you calculate and document hitting it, because that choice effectively limits your options later on for pursuing the advanced credit. Can you break down those initial ASHRA choices within 62.1? Absolutely. So ASHRA 62.1 gives the engineering community two recognized but fundamentally different ways, different methodologies for demonstrating compliance for that prerequisite, EQP2. The first one, and historically probably the most common, is the ventilation rate procedure, often just called VRP.
PRP. Okay.
This is the, let's say, quantitative prescriptive approach. You basically just calculate how much fresh air per person and how much air per square foot is required. You look it up in tables in the standard. It's a pretty straightforward mathematical exercise, relatively speaking. Now, if the design team uses this quantitative VRP for the prerequisite, they maintain the most flexibility for the enhanced credit. It allows them to choose either option 1, which is basically more air, the dilution approach,
Right.
or option 2, which focuses on cleaner air, the purity approach.
Yeah.
So VRP keeps both doors open.
Okay, that makes sense. More flexibility seems good. What's the other method then?
The second method is the IAQ procedure, the indoor air quality procedure.
IAQ procedure. Sounds more involved already.
It is. It's a much more intensive, performance-based, qualitative approach. It requires the design team to actually pre-identify specific contaminants they expect to be present in the building.
Okay.
Then they have to establish target limits for those specific chemicals, those contaminants, and then they need to model and verify that the HVAC system design and the material selections will actually achieve those limits. It's much more complex.
Wait a minute. If the IAQ procedure for the prerequisite is already that much more complicated, requiring chemical modeling, specific targets, why would a design team choose it? Especially knowing it restricts their options for the enhanced credit later. What's the benefit?
That's an excellent question, a really good challenge.
Yeah.
In most, say, typical commercial office spaces, you're right, VRP is usually chosen. It's simpler, it's well understood, engineers are comfortable with it. But the IAQ procedure for the prerequisite, it becomes necessary, or at least highly advantageous, in certain specific building types. Think about specialized research labs, maybe manufacturing facilities where they're dealing with specific chemicals, or even, say, hospitals or schools where managing a particular airborne contaminant like a cleaning agent, a sterilant, a lab reagent is absolutely paramount.
Ah, I see. So if you have a known tricky source of contamination inside.
Exactly. If you have a known complex source, VRP's simple volume calculation might not be enough. Or it might force you to overventilate like crazy to dilute that one specific thing, which kills your energy efficiency. The IAQ procedure lets you surgically target and control that specific contaminant right from the start in the prerequisite design.
Okay, that makes sense for specialized cases.
But you are right, there's a strategic cost. If a project team chooses the IAQ procedure for the prerequisite, the only path available for them to get the enhanced credit, EQc1, is option 2. They can't do option 1.
Only option 2. Wow.
Yeah, they're already committed, philosophically and procedurally, to proving air quality through chemical metrics, through purity. So the volume-based approach of option 1 just doesn't align anymore. It's kind of moot. So this structure, it forces a fundamental design commitment really early on in the project.
So the designer makes this early strategic choice. Either go with the simpler volume math, the VRP, which keeps both enhanced options, option 1 and option 2, open later, or they take the chemical purity path with the IAQ procedure from the start, which is more complex upfront, but maybe necessary for some buildings, and it locks them into option 2 for the credit. Okay. That brings us directly then to option 1, the volume approach. The one teams might favor if they started with that simpler VRP baseline calculation.
Oh, right. Let's focus on that first and maybe more traditional approach to improving air quality. Option 1, increased ventilation. This is the dilution solution, right? The more fresh air fixes its pathway, it earns that one LED point.
Correct.
When you say increased ventilation, what's the actual quantifiable requirement? How much of a bump are we talking about here?
Okay, the core metric is pretty clear. It's a mandatory increase. You have to boost the breathing zone outdoor air ventilation rates by at least 15%.
15%.
15% above the minimum rates that were determined back in the prerequisite calculation, that EQp2 baseline. So for every cubic foot per minute or liter per second that ASHRE 62.1 required as a minimum, your design has to deliver 15% more fresh outdoor air. Okay, 15% minimum. Now here's where it gets really interesting, especially when we think about high performance design overall. That 15% bump gets you the credit point, but lay often rewards going above and beyond. What does it take to really maximize this pathway, to achieve that highly desirable exemplary performance status?
Right, exemplary performance. This often counts for more, maybe an extra point or recognition in the overall LEE certification scheme, depending on the version and specifics. To hit exemplary performance under this option 1, the design team has to push that boundary significantly further. They need to increase the breathing zone rates by a full 30% above the minimum baseline.
30%? Wow, that's double the increase needed for the basic credit point.
Exactly. It's a substantial jump from 15% to 30% more outdoor air than the code minimum.
Okay, a 30% increase in fresh air delivery. That's not just some arbitrary number an engineer pulls out of a hat. That has got to have massive implications for buildings infrastructure, the HVAC system size, and definitely the operating budget, right? What's the primary trade-off here that engineers have to stare down immediately when they consider option 1?
The primary, absolutely undeniable trade-off is energy consumption. There's just no way around it.
Energy, yeah, figures.
You are physically taking 15% to 30% more air from the outdoors. Air that needs conditioning. It has to be heated in the winter, it has to be cooled, and crucially dehumidified in the summer. And potentially filtered more intensely too before it can be delivered to the occupants. This demands significantly larger equipment, bigger air handlers, higher capacity heating and cooling coils, larger fans, maybe bigger ducts. So that means higher capital expenditure, CapEx, the initial cost to build goes up.
Right, bigger stuff costs more.
And then, perhaps even more significantly over the building's life, it means a massive hit to operational expenditure. OPEX. Year after year, you're paying the energy bills to condition and move all that extra air.
So if a project is also trying hard to be energy efficient, maybe they're targeting an Energy Star rating or net zero energy. Option 1 sounds like it could be a real challenge, almost working against those goals.
It becomes a serious design tension, absolutely. You are quite literally working against the energy efficiency goals by imposing this increased fan power requirement and this increased conditioning load from all that extra outside air. The design team has to become extremely clever and efficient in how they deliver that air to try and offset some of that volume penalty. Think about energy recovery ventilators, for instance. They become almost essential to make this option viable from an energy standpoint. You have to recover as much heat or coolness from the exhaust air as possible.
Okay, so that reframes option one. It's not necessarily the easy option just because the calculation seems straightforward. It's more like the strategically expensive operational option.
That's a good way to put it.
Let's get specific on the delivery mechanism then. You mentioned breathing zone, outdoor air ventilation rates. What exactly are we measuring there, and why is that distinction breathing zone so important?
Right, the breathing zone. This is defined generally as the region within an occupied space where occupants are most likely to be breathing. Think roughly from, say, 3 feet to 6 feet above the floor when seated, maybe slightly higher when standing.
Where people actually live and work.
Exactly. We are not just measuring the total volume of air pouring out of the central HVAC unit way back in the mechanical room. We're interested in the effective fresh air delivery at the point of use, within that zone where people are inhaling. And this is critical because of things that can go wrong with air distribution. Phenomena like air stratification, where warm air pools near the ceiling and cool air near the floor, or short-circuiting, where supply air rushes straight to the returned grill without mixing properly, or just generally poor at mixing in the space.
Ah, okay. So you could be supplying the right total volume, but if it's not getting to where people are.
Precisely. If you push 30% more air into a supply duct, but the diffusers, the air terminals in the room, are positioned badly or the airflow pattern is wrong, that extra freight air might just bypass the occupants entirely. It might hug the ceiling and go straight back into the return plenum without ever properly mixing and diluting the contaminants down where people are breathing.
So the design isn't just about the fan size and the CFM number. It's about effective distribution and making sure that extra air actually does its job.
Exactly. It's about ventilation effectiveness, not just ventilation rate.
Okay. And that leads directly to the crucial special requirement you mentioned for this credit. These increased outdoor air rates, this 15% or 30% bump, must be provided to 95% of all regularly occupied spaces.
Yes, 95%.
95% coverage. That sounds like it means almost total coverage of where people actually spend their time. What is the engineering complexity involved in actually verifying that 95% threshold is met? That sounds tricky.
Verification of that 95% is definitely the commissioning challenge. It demands meticulous documentation during design and then rigorous testing and balancing during commissioning after construction. So boots on the ground with airflow meters. Absolutely. You can't just assume based on the design drawings that every room gets its calculated share. You need actual airflow readings taken at the supply air terminal units in a representative majority of the regularly occupied spaces, offices, conference rooms, classrooms, labs, whatever the building function is. That 5% allowance, the wiggle room, is there realistically to account for spaces that are maybe truly transient, like corridors, or perhaps architecturally very challenging to ventilate perfectly without some major compromise. Think of a tiny storage closet, or a niche mechanical area that's technically occupied sometimes but not regularly, or maybe a very small, very low occupancy break room, where adding the extra ductwork would be disproportionately complex and costly compared to its use.
Okay, so it acknowledges some practical limits.
Right. But for the core areas, the spaces where people are spending significant time, maybe 4 to 8 hours a day, you must be able to prove with data that the elevated ventilation rate, that minimum plus 15% or 30%, is being consistently delivered to the breathing zone.
This sounds like it could be a particular nightmare for variable air volume systems, VAV systems, which are super common in office buildings. Their whole point is that the airflow changes, right? It throttles down when the room doesn't need cooling or heating. How do you ensure that 95% of those spaces maintain a minimum 15% or 30% increased outdoor airflow, even when the VAV box itself is throttling way down because the thermostat is happy?
You've hit on precisely the core control challenge with option 1 in VAV systems. It's a major hurdle. The system must be designed and controlled to decouple the thermal control, maintaining temperature, from the minimum ventilation requirement.
Decouple thermal from ventilation.
Okay, exactly. The VAV system's control sequence has to be programmed very carefully, so that when a space is thermally satisfied, meaning the temperature is stable, the thermostat isn't calling for cooling, and the VAV box damper starts to close down to reduce total airflow. The system still ensures that the minimum required outdoor air ventilation for that space, the amount needed for breathing based on occupancy, plus the 15% or 30% enhancement, is maintained.
How do they do that? Does the main air handler just keep pumping in the higher outdoor air percentage regardless?
Often, it involves setting a minimum damper position on the VAV box itself, ensuring it never closes below a certain point needed for ventilation, even if it means slightly overcooling or reheating sometimes. Or, more sophisticated systems use what's called demand-controlled ventilation, DCV, coupled with precise minimum outdoor air calculations at the main air handler unit, AHU. The AHU might monitor CO2 levels or occupancy sensors in the zones and adjust the total outdoor air intake dynamically, while ensuring each active zone's VAV box maintains its minimum required outdoor airflow. It requires really sophisticated digital controls, sequences of operation that monitor both temperature and minimum ventilation rates simultaneously for potentially hundreds of zones. It definitely pushes the control sequence engineering and the commissioning effort to its limits.
Wow, okay. So option one, powerful in concept, just flush contaminants out with the sheer volume of fresh air, but it comes with a potentially very high price tag in ongoing energy consumption, and it demands extreme rigor in system sizing, sophisticated controls, especially for VAV, and meticulous commissioning to actually prove that 95% coverage in the breathing zone.
That sums it up well. It's conceptually simple, but technically demanding to execute correctly and efficiently.
All right, let's flip the script then. Let's move to the alternative path, option two. So we're shifting gears now. We're moving away from the quantitative volume question, how much air, the defined option one, and we're entering the qualitative purity world, what's in the air, with option two.
Exactly.
This is option two, enhanced indoor air quality design. And you said this one focuses more on source control, preventing pollution in the first place, and maybe hyperfiltration to earn that same single LED point. What's the requirement framework look like here?
This framework really represents a significant philosophical shift. It moves away from dilution as the primary strategy and towards achieving absolute contaminant control at the source, or through removal. Remember how the IAQ procedure for the prerequisite, if chosen, was based on hitting baseline contaminant targets found in AHHRA 62.1/2022, specifically in tables 6-5 and 6.6.
Right, those baseline chemical targets.
Well, option 2 for the credit requires the project team to design, build, and then verify systems that meet lower, significantly stricter design limits for specific key pollutants. These stricter limits are listed specifically in the LEED V5 standard itself, in Table 1 for this credit.
Ah, okay, so LEED sets its own tougher chemical benchmarks here below the AHRA baseline.
Correct. The core task becomes demonstrating first through design specifications for materials and systems, and then through verification, potentially post-occupancy testing, that the building's material choices, its filtration systems, maybe specific ventilation strategies, and equipment choices actively inhibit, filter, or control these specific pollutants down to these exceptionally stringent, below baseline standards defined by LEED.
This really does sound like chemical precision engineering for a building. We absolutely need to go through these specific limits from that LEED V5 Table 1 because these hard numerical benchmarks are what really define the difficulty, the challenge of achieving this credit option. Let's start with airborne particulates, the tiny stuff. First up, let's tackle that microscopic menace you hear about a lot, PM2.5. What is the specific LEED V5 limit for PM2.5 under option 2, and why is hitting that number considered so demanding?
Right, PM2.5. It stands for particulate matter that is 2.5 micrometers or smaller in aerodynamic diameter, so incredibly tiny particles.
Smaller than dust, pollen.
Much smaller. These are the particles often associated with smoke, haze, vehicle exhaust, industrial processes. And they're considered highly hazardous because their small size allows them to bypass the body's natural defenses in the nose and throat, penetrate deep into the lungs, and potentially even enter the bloodstream, causing respiratory issues, cardiovascular problems, and other systemic health effects.
Okay, clearly bad stuff. What's the limit LED sets?
The LEED V5 enhanced design limit for PM2.5 under option 2 is set at 10 gMerio. That's 10 micrograms per cubic meter of air.
10 micrograms per cubic meter. Okay, 10 gMerio. That sounds low. But to put it in context for us, how does that 10 gMerio compare to, say, typical outdoor air or maybe other health guidelines?
It is exceptionally stringent. For comparison, the World Health Organization, the WHO, currently recommends an annual average exposure guideline limit of 5 bazinas. But their 24-hour average exposure guideline is 15 GMAs.
Okay, so 15 for a 24-hour WHO guideline.
Right. An LED is setting a design target of 10 GMAs. This means the building systems must be designed to maintain air quality near or below this pristine condition consistently, not just as a daily average. Think about typical urban outdoor air quality. Especially near busy roads or during wildfire smoke events or periods of atmospheric haze, The outdoor PM 2.5 level can easily spike to 50 dimers on 100 GMs or even much higher in severe conditions.
Right, much higher than 10.
Exactly. So achieving a constant 10 GM indoors means that even if the outdoor air quality is quite poor, the building's ventilation and filtration system has to effectively scrub that incoming air clean enough to reduce the particulate concentration by, say, 80%, 90%, or even more upon entry.
Wow. How do you achieve that level of cleaning?
This really necessitates the use of very high-efficiency particulate air filtration.
Yeah.
We're likely talking about filters rated MIMSI-16 at a minimum, or potentially even HEPA-equivalent filtration, especially if the outdoor air is frequently bad.
MRF 16 or HEPA. Those are serious filters.
They are. And again, just like with option 1's increased volume, these high-efficiency filters introduce their own significant fan energy penalty. They create more resistance to airflow, meaning the fans have to work harder, using more energy, just to push the air through. So here you're trading the energy penalty of dilution, option 1, for the energy penalty of extreme filtration, option 2.
Okay, so PM 2.5 at 10 GMRA means serious filtration and the energy that comes with it. Next on the list from LEED's Table 1, let's look at a chemical pollutant. One we often forget about, maybe because it comes from the products right there inside the building with us, formaldehyde. What limit is LEV5 setting for this one?
Formaldehyde. Yes, it's a notorious volatile organic compound, a VOC, and it's problematic because it off-gases it's released into the air from so many common building materials and furnishing products.
Like what kind of products?
Oh, many things. Composite wood products like particle board or MDF used in furniture and cabinetry, certain types of insulation, the glues and adhesives used in flooring and assembly, some paints and coatings, even fabrics and carpets can release formaldehyde. So, achieving control over formaldehyde indoors is generally less about filtering it out, although activated carbon filters can help somewhat and much more about source control. Preventing it from getting into the building's air in the first place by carefully selecting materials.
Source control. Makes sense. What's the LEED number?
The DV5 enhanced design limit for formaldehyde under option 2 is 20 Nijonio, 20 micrograms per cubic meter.
20 micrograms per cubic meter for formaldehyde. Now, this requirement must drastically impact the whole specification and purchasing phase of the project, right? It's not just about the HVAC anymore.
Absolutely. It ripples through the entire design and construction process. Think about the sheer complexity of materials that go into a large commercial building project. You've got thousands of different products.
Yeah.
Adhesives for flooring, sealants around windows and plumbing fixtures, laminate materials for countertops and cabinetry, paint for every wall, insulation, furniture, the list goes on and on. If you want a design to maintain a 20 Warnell limit for formaldehyde, every single one of those potential emitting materials has to be vetted. You need to ensure it's certified as low VOC or, ideally, formaldehyde-free.
So standard off-the-shelf construction products in many categories might just be ruled out immediately.
Very likely, yes. It necessitates extremely detailed documentation and tracking. Often, you'll need to rely on third-party certifications programs like Green Seal, SCS Global Services Indoor Advantage Gold, Floor Score for flooring, or demanding specific test reports based on protocols like the California Department of Public Health, CDPH, Standard Method V1.2 for VOC emissions, for basically every interior finishing product and furniture item specified in purchase. The materials specifier's job, or the architects or interior designers, it really turns into that of a chemical detective, meticulously tracing the source, the composition, and the verified off-gassing profile of every single component that goes inside the building envelope.
That sounds like a massive undertaking in coordination and paperwork alone.
It is. It requires buy-in and diligence from the entire project team, including the general contractor and all the subcontractors who actually purchase and install the materials.
Okay, formaldehyde at 22 remember means intense material scrutiny. What's the third major pollutant targeted by option 2 in EDV5?
The third one is ozone, specifically indoor ozone.
Ozone. I usually think of ozone as an outdoor air pollution problem, like smog.
It is a major outdoor pollutant, yes. But ozone can also be a significant indoor air contaminant. It's a highly reactive gas and a known respiratory irritant.
Okay, so if it's not coming in from outside, where are the sources of ozone inside a building?
Indoors. The sources are often specific types of equipment. Things like older laser printers and photocopiers can generate ozone as a byproduct of their high-voltage processes. Also, and this is a tricky one, certain types of electronic air cleaners or air purifiers actually intentionally generate ozone, claiming it helps purify the air or remove odors.
Wait, they generate ozone on purpose?
Some older or less reputable ones do, yes.
Yeah.
It's a highly inadvisable practice in occupied spaces, according to most health organizations, because ozone itself is harmful to breathe.
Yikes. Okay, so what is the LED limit for indoor ozone under option 2?
The LEED5 enhanced design limit for ozone is set at a staggeringly low level, 10 ppb, that's parts per billion.
10 parts per billion, not micrograms per cubic meter like the others, but parts per billion. That numerical specificity, ppb, it really speaks volumes about the level of air chemistry control required here. Why the emphasis on parts per billion for ozone?
Because ozone is such a powerful oxidant and irritant, even very tiny concentrations, measured in parts per billion, can be irritating to the respiratory system or trigger asthma attacks in sensitive individuals. Maintaining a design target of 10 ppb is essentially aiming for background noise level, close to what you might find in truly pristine outdoor air, far from pollution sources.
So how does a design team ensure they stay below 10 ppb?
It demands a holistic design approach, again focusing on source control. Primarily, it means the design team must specify and mandate that no intentionally ozone-generating equipment is installed anywhere within the occupied spaces of the building.
Banning certain types of equipment.
Effectively, yes. Banning ozone-generating air cleaners is key. And if high-volume printers or copiers known to produce ozone are absolutely required for the building's function, they must be housed in dedicated rooms. These rooms need their own independent exhaust systems that vent directly outdoors, preventing any ozone from migrating into general circulation air. Furthermore, any proposed air purification system, whether integrated into the HVAC or standalone, must be carefully vetted to ensure it uses non-ozone generating technology like high-efficiency filtration or maybe UVGI, ultraviolet germicidal irradiation, done properly within the ducts, not ozone generation.
So it's really a design standard that effectively bans or isolates several common office and sometimes even cleaning technologies that might produce ozone.
As a fair summary, achieving 10 ppb consistently requires proactive elimination of potential indoor sources.
Okay, let me try to quickly summarize option 2 then. We are talking about deliberately engineering a specific chemical environment inside the building. We're targeting PM 2.5 down to 10 micrograms per cubic meter, which demands extreme filtration. We're targeting formaldehyde down to 20 micrograms per cubic meter, requiring meticulous low VOC material sourcing and vetting. And we're targeting ozone down to 10 parts per billion, necessitating the exclusion or isolation of ozone-generating equipment.
Right.
These are benchmarks that require, it seems, exceptional quality control throughout design and construction, hyperfiltration strategies, and materials management and procurement processes that go far, far beyond standard architectural specification and construction practice.
That's absolutely right. Option 2 is a deep commitment to chemical purity and source control. So we step back and try to connect all this back to the bigger picture, especially for you listening. This LED V5 Enhanced IAQ credit, EQc1, it really presents designers and building owners with two fundamentally different philosophies for achieving better occupant health through air quality. And, importantly, each comes with its own significant financial and engineering burden.
Two different paths, two different sets of challenges.
Exactly. Option 1, increased ventilation. It's fundamentally about dilution. We accept that contaminants might be present, but we try to solve the problem by increasing the volume of outdoor air, flushing the indoor air constantly with 15% to 30% more fresh air than the minimum required. The strategic cost here, as we discussed, is primarily operational expenditure, the ongoing OPEX, due to those perpetual high energy loads for fans and conditioning all that extra air. And the engineering challenge is verification and control, ensuring that 95% coverage is actually maintained in the breathing zone consistently, even in complex dynamic systems like VAV.
Okay, that's option 1. Dilution via volume, high OPEX, control complexity.
Then you have option 2, enhanced indoor air quality design. This is about purity and source control. We try to solve the problem by preventing contaminants from existing at high concentrations in the first place, or by removing them very effectively. This involves using hyperfiltration for particles and meticulous material sourcing and equipment selection to limit chemical off-gassing and generation. The strategic cost here tends to be weighted more towards the initial capital expenditure, the CapEx. You're paying more upfront for superior filtration equipment, for the extensive materials testing and documentation, and often a price premium for certified low VOC or no VOC products. The engineering challenge here is achieving that chemical precision designing and building to meet those incredibly low parts per billion or microgram per cubic meter limits.
Option 2, purity via control, high CapEx, chemical precision challenge.
So that's a good way to summarize the trade-off.
And I guess the beauty of the standard, maybe, is that the unifying goal remains constant, regardless of which path is chosen. It's to better protect the health of building occupants. That's the stated intent.
Absolutely. That's the driving force behind the credit.
So this deep dive really shows that achieving a LEED V5 air quality credit like this, it's not trivial. It's not just checking a box. It's an act of detailed strategic engineering. It forces the design team and the owner to make a conscious decision about where they want to invest their resources, their time, their money, and their project complexity. Do they invest it in massive airflow systems and the energy run them, option one, or do they invest it in precise chemical vetting, hyperfiltration, and source control, option two?
It forces that strategic choice, yes.
So so what for you, the listener, I think, is really understanding that this is the cutting edge of healthy building design right now. This knowledge highlights the profound difference between a building that merely meets the minimum ASHRE code, which, let's be clear, is designed primarily for legal safety and basic comfort, and a building that actively, intentionally designs for optimal human health, for better cognitive performance, for long-term well-being by ensuring superior air quality. Earning this EQc1 credit signals that the health of the occupants was considered a primary engineering goal, woven into the very fabric and systems of the structure, going far beyond just meeting typical regulatory requirements.
And that granularity, especially the chemical specificity we see in option 2,
Yeah.
it really sets a new performance benchmark for the entire industry. Imagine being the project manager responsible for tracking material sourcing and submittals to ensure compliance with that 20 germatoformaldehyde limit.
Yeah, the logistics sound intense.
It requires intense coordination between the architect, the interior designer, the general contractor, the purchasing agents, and every single trade subcontractor who might bring an adhesive, a sealant, a paint, or a piece of composite wood onto the site. It fundamentally changes the supply chain management and quality control needed during construction.
And presumably it gives you more confidence that the building doesn't just look healthy on paper during the design phase, but is actually delivering that pristine air quality when people move in and start living and working there.
That's the goal, certainly. Verification, potentially through post-occupancy air testing, is often part of demonstrating compliance for option 2, aiming to confirm those low contaminant levels are actually achieved in practice. Now, this raises a really important, maybe provocative question for the future, thinking about the inherent differences between these two options, option 1 and option 2. As we face increasing challenges with outdoor air quality in many parts of the world due to climate change impacts like wildfires, increased urbanization leading to traffic pollution, industrial emissions, persistent photochemical smog, those days where the outdoor air quality index is poor or even hazardous.
Right, happening more often, it seems.
Exactly. In that context, can high-performance building design continue to rely solely or primarily on just increasing the volume of outdoor air being brought inside, option 1, to achieve truly enhanced indoor air quality? If the air outside is already compromised, is bringing in 30% more of it always the best health strategy, even if filtered?
Good point. Dilution only works if what you're diluting with is clean.
Precisely. Or is the future of truly exceptional human health in buildings inevitably more reliant on creating robust, highly filtered, high-performance building enclosures that focus heavily on source control and chemical precision inside, like option 2, essentially treating the indoor environment as a protected bubble, meticulously controlling what comes in and what's generated inside, even if that path is technically and financially more demanding up front?
So dilution versus purity. Maybe purity becomes more important as the outside world gets dirtier.
That's the question to ponder. This duality, the tension between relying on outdoor air volume versus relying on indoor purification and control, is something really important for you, the listener, to consider as these green building standards and our understanding of building science continue to evolve in response to pressing global environmental and health challenges. Where should the focus be in the next generation of buildings? Hashtag outro.
Wow, that was definitely an expansive look into the strategic choices, the trade-offs, and the really granular technical demands of high-performance indoor air quality design under LEV5. Just to quickly recap the key takeaways for everyone listening. Achieving this Enhanced Indoor Air Quality Credit, EQc1, requires first exceeding that ASHRAE 62.1 2022 baseline, EQP2. Then, you have to choose one of two pretty demanding paths. Path 1, option 1, is the dilution strategy. Commit to at least a 15% minimum increase in breathing zone outdoor air ventilation, delivered to 95% of occupied spaces. Go up to 30% for exemplary performance, but brace for the energy impact. Path 2, option 2, is the purity and source control strategy. Design and build to meet LEED's own strict chemical limits, specifically 10 micrograms per cubic meter for PM2.5, 20 micrograms per cubic meter for formaldehyde, and just 10 parts per billion for ozone. This means intense filtration and meticulous material selection.
That's it. And that choice you make between investing in high-volume airflow and its operational expense, or investing in high-precision chemical control and its capital expense, is really one of the most fundamental strategic decisions in modern, health-focused building science. LEED V5 just provides the exact, demanding numerical requirements for defining success down either path.
Really fascinating stuff. Thank you so much for sharing the sources and walking us through the details that made this deep dive possible.
My pleasure.
And for everyone listening, if you enjoyed this exploration into the nuts and bolts of LEED V5 and the science of building health standards, make sure to subscribe. That way you'll hear more about this constantly evolving world of high-performance design.